Hello. Today we're going to explore how temperature influences chemical changes. Have you ever noticed how some foods cook faster when the temperature is higher? Or how some reactions seem to happen more quickly on a hot day? That's because temperature plays a crucial role in how fast chemical reactions occur. Think of temperature as a measure of how much energy the molecules in a substance have. When you increase the temperature, you're essentially giving those molecules more energy to move around and bump into each other. When you cool down the particles, their motion decreases and they bump into each other less often. Remember, temperature is a measure of the average kinetic energy of the particles of a substance. At lower temperature, the particles have less kinetic energy on average than the substance at a higher temperature. But remember, temperature is an average measurement. That means at higher temperatures, the spread or range of kinetic energies of the particles that make up the substance is greater than the particles at lower temperatures. Those particles' kinetic energy are much closer together at lower temperatures. Note how the higher temperature graph is more spread out than the lower temperature graph, since the particles of the substance have a wider range of kinetic energies, with some having small kinetic energies in motion, others having kind of the average, and still others having much greater kinetic energies and motion than the average or the lower kinetic energy particles. Now, for a chemical reaction to happen, the molecules involved need to collide with each other with enough energy to break their existing bonds and form new ones. This energy is called the activation energy. When you increase the temperature, you're increasing the number of molecules that have enough energy to overcome this activation energy barrier. This means that more collisions will be successful, leading to a faster reaction rate. Let's look at a few examples. First, consider a simple chemical reaction, like the fizzing of an antacid tablet in water. When you add the tablet to water, it starts to dissolve and react, releasing carbon dioxide gas. Now, if you were to heat up the water before adding the tablet, you'll notice that the fizzing starts much faster. That's because the higher temperature gives the water molecules more energy, leading to more frequent and energetic collisions with the antacid tablet. Another example is cooking. When you cook food, you're essentially speeding up a series of chemical reactions that change the food's texture, flavor, and nutritional value. Cooking at a higher temperature provides more energy to the molecules in the food, causing the reactions to happen faster. That's why your food cooks more quickly in a hot oven or on a high temperature burner. However, it's important to note that temperature can also have a negative effect on some chemical reactions. For example, high temperatures can cause certain enzymes, which are biological catalysts, to lose their shape and function. Just like the white of an egg changes from clear and a liquid to a solid and white when heated, the structure and function of some enzymes change and affects reactions. This can slow down or even stop the chemical reactions they catalyze. This is not bad when we want to cook an egg for eating. However, our bodies contain proteins much like the egg white. If a person becomes too hot, these proteins can break down just like the egg white and become useless for the intended body functions. Not a good thing at all. So while temperature can speed up many chemical reactions, it's essential to find the right balance. Too high a temperature can sometimes have the opposite effect. In conclusion, temperature plays a significant role in influencing the rate of chemical reactions. By understanding how temperature affects these reactions, we can better control and manipulate them in various applications, from cooking to industrial processes. That's all for today. Thank you for watching.